For countless millennia, human beings and their distant ancestors have gazed up at the night sky, dreaming about the possibilities of dancing across the cosmos with the stars that twinkled above. In September of 1977, the chance to turn those dreams into a reality came true when a space probe destined for greatness was launched into the vastness of our solar system, on a voyage to give us a better glance at the many mysteries we've been staring up at for eons. Enter Voyager I, one of the greatest examples depicting the intensity of space exploration that would embark on a near 50-year adventure full of twists and turns and discoveries we can only describe as a miracle. This is its story. Like many early initiatives enacted to further our understanding of the universe and celestial bodies surrounding us, Voyager I's journey begins in the 1960s when NASA approved a program to fulfill their grand tour of all the planets in our solar system. Simultaneously, astronomers were receiving information back from the space probe Pioneer 10, the first ever craft to explore and study Jupiter. They received new information about the volatility of Jupiter's atmosphere and the high levels of radiation, and knew there wasn't enough time to update Pioneer 11 before its launch for a similar mission. Thus heads turned to the Mariner program, a NASA initiation that oversaw successful probes to Mercury, Venus, and Mars in hopes to complete the Grand Tour's installments at both Jupiter and Saturn. NASA promised Mariner 11 would be the next space probe to venture to Jupiter and beyond. But as fate would have it, budget cuts at NASA prevented any type of exploration outside of flybys, and with the desire to learn more about the gas giants, NASA shifted its engineering efforts to a new program titled Voyager. With the Voyager program, astronomers hoped to embark on a new mission prioritizing the planets in the second half of the solar system. They wanted to engineer state-of-the-art probes featuring technology that would allow future scientists to study their data for half a century. After new funding was confirmed by NASA, their top flight engineers got to work, quickly developing a pair of twin probes appropriately titled Voyager I and Voyager II. Featuring the necessary wavelength readers, bulky communication systems, and digital computers with photography capabilities. Astronomers hoped to send both of their new Voyager space probes to Saturn and Jupiter, but needed one of them to simply fly by and reach the ice giants for a deeper study of Uranus and Neptune. Thus they programmed Voyager II to launch 2 weeks prior to Voyager I on August 20th, 1977, clarifying that it would take a longer route to reach the gas giants, but a more optimal route to reach the ice giants earlier in its lifetime. 16 days later, on September 5th, 1977, Voyager I made its grand launch, taking off aboard Titan III Centaur at Cape Canaveral Air Force Station in Florida. Entering space without a hitch, Voyager I was well on its way to the gas giants. A little over 3 months into its expedition, and the space probe finally reached the asteroid belt, a volatile period of its journey that would last almost 3/4 of a year. Voyager I overtook its sister spacecraft 9 days later on December 19th, 1977, and after exiting the asteroid belt in September of 1978, the space probe finally initiated its Jupiter observational window in January of 1979. The official phase of Jupiter's observation by Voyager I began on January 6th, when the space probe started its photography of the planet's magnetosphere. For the next 2 months, Voyager I approached the biggest planet in our solar system, gathering as much data as it could, until March 5th, 1979, when it reached its closest proximity to the gas giant the entire mission would allow for, finally making contact with the Jovian system and Jupiter's arena of 80+ moons and moonlets. Within the next 48 hours, at approximately 5 minutes and 26 seconds past noon and 217,000 miles from Jupiter's core, Voyager I took some of the most detailed photographs of Jupiter astronomers couldn't even imagine, using the 2-day window to capture the Jovian system in all of its unrealized glory. Earlier that morning, the space probe took photographs of the moon Amalthea, followed by close-range pictures of Jupiter's other famous natural satellites, with Io at 1514 and Europa at 1819 respectively. The following day, Voyager I wrapped up its close-up photography with the moon Ganymede, the largest moon in our solar system at 215, and Callisto at 1708, Jupiter's third largest moon and the potential future home base for more in-depth studies of the Jovian system. By April, Voyager I had ventured deep enough into the outer rim, and its observation of Jupiter was no longer productive. However, the intensive flyby did shine a light on data points NASA was previously ignorant to. The biggest discovery was the faint yet fully formed planetary rings surrounding Jupiter, a planet once thought to be without any halos. The rings, while only made up of mostly dust particles, appeared red in colour, except for the innermost halo ring, which appeared blue. Right outside of the ring's foremost belt, Voyager I detected 2 new satellite moons, eventually called Adrastea and Metis, with a third, called Thebe, found later between 2 established moons. They were the first of Jupiter's natural satellites to be revealed by a space probe, rather than someone or something here on Earth. While not as monumental as the planetary rings, the most surprising of all the discoveries across the Jovian system was Voyager I's finding of present volcanic activity on Io, the closest of the Galilean moons to their home planet. These volcanic discoveries were the first of their kind on any celestial body across the entirety of the cosmos outside of Earth. The active eruptions released high enough outputs of sulfur, sodium, and oxygen, 3 materials found all the way at the end of the Jovian magnetosphere. The time spent around Jupiter may not have seemed long, but it was only the first step of many in Voyager I's galactic adventure. And with how much knowledge it had already provided, it was only a sign of things to come when compared to the rest of the excursion. By the middle of April 1979, Voyager I wrapped up its Jovian flyby and began its transition to the Saturnian system, embarking on a 16-month trip through August of 1980 when its long-distance study of Saturn went underway. Far-off data was collected for nearly 3 months until November the 12th, when the space probe finally reached the Saturnian system. At roughly 5:41, Voyager I conducted its long-awaited flyby of Titan. It had been previously established that Titan, the second largest moon in our entire solar system, contained an atmosphere, and further photos and studies conducted by Pioneer 11 suggested Titan's atmosphere was complex and quantitative. NASA was determined to get a better look and shifted Voyager I's trajectory to fly even closer to Titan, altering its course enough to prevent it from being able to travel the solar system's outer plane and reach the likes of Uranus, Neptune, and Pluto. It was a risk astronomers were willing to take, as they figured that whatever lay on Titan was much more important than doing exactly what Voyager 2 would do in years to come. Luckily for NASA and the rest of the astronomical community, the gamble paid off. Voyager I was able to get new readings for Titan's atmosphere, whether it be density or composition. It also confirmed the complex nature of the thick haze surrounding Saturn's largest moon, revealing that no visible wavelengths can penetrate the surface. Taking the data readings into consideration, there was a good chance vast lakes made up of liquid hydrocarbons could exist below the atmosphere, but Voyager I wouldn't be the probe to observe it. The spacecraft also unveiled a few other major discoveries in the Saturnian system. It learned that Saturn's helium content was much lower than previously thought, as astronomers believed it would align more closely with Jupiter or the Sun's helium output. Rather, astronomers now believe the helium they once thought could be found on the surface of Saturn has sunk deep within its core, explaining why the energy produced by the planet itself was much greater than the energy that would be provided by the Sun. Voyager I also recorded some of the strongest winds ever documented across the solar system. Saturn had always been known as a volatile gas giant with winds estimated at high speeds, and the space probe confirmed that when it picked up winds blowing at nearly 1,100 miles per hour, or 500 meters per second. In the end, Voyager I accomplished exactly what it set out to do: study the cosmically rich, yet still enigmatic systems of Jupiter and Saturn while photographing and recording radio signals simultaneously, surviving the unknown of interplanetary travel. Yet despite the mere 3 years spent approaching and researching the gas giants, Voyager I's journey was only beginning, as it left the Saturnian system in November of 1980 and embarked on a 10-year trek to the outskirts of our solar system and into interstellar space. Before the fantastic voyage of Voyager I, no man-made object, let alone a space probe, ever entered interstellar space, the stretch of the universe that exists beyond our solar system. Voyager I was well on its way to fulfilling that achievement, but not before taking one of the most important and breathtaking photos in the history of space exploration. On February 14, 1990, nearly a decade after leaving Saturnian airspace, Voyager I captured what is now colloquially known as the family portrait, a mosaic of 60 frames of photos, including 6 planets in our solar system with their positions and partial backgrounds detailing a realistic portrayal of their appearance from the outside. No photography feat had ever been accomplished before, as it took place approximately 6 billion kilometers from Earth. One of the components to family portrait included Pale Blue Dot, one of the most famous space-related pictures ever recorded, depicting Earth as less than a pixel in size with a backdrop of the Milky Way's foreboding emptiness, the perfect reminder for how small and insignificant we truly are. Another 8 years passed and Voyager I started to approach an exit from the solar system to enter interstellar space. By this point, both its cameras and ultraviolet spectrometer were shut down, either intentionally to save power or by the failing of the onboard powering systems. Despite this, Voyager I continued to propel through space at 61,197 kilometers per hour, or 38,026 miles per hour. It entered termination shock in around 2003, where solar winds hit subsonic speeds that are slower than the speed of sound. Between 2006 and 2010, the space probe reached the heliosheath, also called cosmic purgatory, where these speeds begin to influence solar particles being reflected back into the solar system due to pressure from interstellar space. In this region of space, Voyager I detected levels of Lyman alpha radiation, the first of its kind to be found in the Milky Way after it was thought it only existed in far-off galaxies. This is also where a good chunk of the scientific instruments aboard the probe began to shut down. A couple of years later, in the summer of 2012, Voyager I crossed the heliopause, where the conflicting interstellar and solar winds reached equilibrium. It was the first ever object to do so, and officially entered interstellar space for the first time in history in August of that year. Since this grand cosmic event, Voyager I has seen more and more of its instruments disabled due to dying energy sources. However, it has led to further discoveries about interstellar space, such as its unexpected density readings and newfound interstellar sounds, things we would have never discovered without the space probe's unparalleled survival. The fate of Voyager I is still unknown to this point, as it has been since its initial launch in September of 1977. 45 years later, it's still propelling through space at intense speeds, and at this point in time will remain the furthest man-made object from Earth throughout all of the cosmos. Not even New Horizons, the space probe launched in 2006 to study the likes of Pluto and the edge of the solar system, will pass Voyager I due to boosts from heliocentric velocities as a result of multiple planetary flybys on the behalf of Voyager. In the end, Voyager I will become a fleeting vessel with no remaining research value. It's estimated that between 2025 and 2036, all the instruments still functioning on the probe will shut down for good, as the power supply will hit zero without any means of resupplying out in unmanned space. Despite the lack of energy, however, Voyager I's excursion will continue. In around 300 years, the probe's trajectory will take it to the Oort cloud, a theoretical collection of ice-ridden planetesimals, solid objects in the shape of a disk. The Oort cloud is merely a projection made by astronomers to explain long-period and Halley-type comets continuously zipping across the solar system, but sadly there will be no way to record their existence by that time. If Voyager I survives the 30,000-year journey through the cloud and remains free from impact, it would pass within 1.6 light-years of the star Gliese 445 in 40,000 years, the closest we've been to another star in the galaxy. After that, it will wander the Milky Way for what is calculated to be almost eternity, as the time it would take for the probe to reach another galaxy at the speeds it is travelling would be too high to count. The one glimmer of hope we have aboard Voyager I to make an impact on the universe beyond its functionality period is the Golden Record, a gold-covered audiovisual disc embedded with records of life on Earth, such as generational music recordings from cultures around the globe, greetings recorded in 55 different languages, photos of daily activity, and various bits of scientific information. The record was stowed on Voyager I in hopes that if life does exist somewhere out in the galaxy, a life form might bump into the probe and discover what it's like back here on Earth. While it's mostly thought of as a joke rather than an expectation, it's comforting to think that a microcosm of who we are on Earth is represented out in the cosmos. It makes Voyager I the perfect symbol of humanity, enduring journeys of epic proportions with hopes that a dream may come true, however unlikely it may be. Its voyage is one of inspiration and hope, and may it be the reason you set out to accomplish something fulfilling and courageous, whether it be today or years into the future. Regardless of who you are or where you are going, there is hope, just like there is with Voyager I.